Recording started.
Okay, good evening, everybody. Once again, this is Professor Ayorinde, welcoming you to another session of organic chemistry. Before we start the session, a couple of announcements. Our own work assignment for the next 2 weeks will be posted tonight, and those will be for chapters 20 and 21, and both will be due any time from now till the next 2 weeks. The last due date for those two homework assignments will be March 19. That's Monday, March 19. And also the next online review session will be next Wednesday. That is March 9. Okay. Is that right? March 9? Next Wednesday. No, March 7. Sorry about that. That will be March 7. That will be the next online review session. Okay, for today we are going to start the discussion on chapter 20, which is concerned with the chemistry of carboxylic acid and nitriles. Emma, can you go ahead and read for us what this chapter is all about?
Nomenclature, synthesis of carboxylic acids, reactions of carboxylic acids, synthesis of nitriles, reactions of nitriles, and spectroscopy.
Okay, very good. So in other words, for this chapter we are going to discuss all of these topics, nomenclature, synthesis, and reactions of carboxylic acid and nitriles. Of course, upon completion of this chapter, there are certain skills or competencies that we expect of you, and so this slide here simply lists a few of those competencies. Jessica, can you give us a couple of them?
Right, I technically carboxylic acid, right, especially for carboxylic acid,
okay, very good. In other words, at the end of this chapter, you should be able to perform all of these activities on this slide. Okay, so because the question that comes to mind at this point, what are carboxylic acid and nitriles? By now, I'm sure most of you already know what this type of compounds are. So hopefully this will be sort of like a review for just about all of you here. Of course, we know carboxylic acid are compounds that are characterized by the presence of what we call a carboxyl group. We refer to this as a carboxyl group. As you can see in the carboxylic acid, which containing the carboxyl group, you have the carbonyl group, which is a carbon-oxygen double bond, bonded to an hydroxyl group, and the carbonyl group is in turn bonded to a carbon atom. With respect to the nitriles, you have a carbon-nitrogen triple bond, in which you have carbon triply bonded to nitrogen, and we refer to this group as a cyano group. Okay, so you have a cyano group bonded to a carbon atom. So these are the two functionalities that you find in both carboxylic acid and nitriles. But before we go to the nomenclature of these types of classes of compounds, what I want us to do today is to begin to take a look at the importance of these classes of compounds. And to do that, I want you to take a look at this molecule here. If you take a look at this molecule, I have this here. Of course, we know this molecule here is a carboxylic acid. Why do we say this is a carboxylic acid? Why do we call this a carboxylic acid? It contains a carboxyl group. Very good. Now, the importance of this molecule, I'm sure most of you have used this molecule before. This is a very important pharmaceutical drug. How many of you have heard of ibuprofen? How many of you? Okay, most of you have heard of ibuprofen. Very important analgesic drug. Some of you might have heard of it as Advil. How many of you have heard of Advil? Okay. Or Motrin? The same molecule, right? Now, you say, why do I bring this up? I want us to now begin to look at how do we design, synthetically design the production of this type of molecules. Say, for example, at this point, I expect that you guys know enough organic chemistry now that if you now go to a pharmaceutical company, they want to employ you and they want to test your knowledge of organic chemistry. They say, okay, let us see how much organic chemistry do you know. They give you this molecule here. Say, give us a synthetic design for this molecule. Starting from here. Starting from here. So I want to take a few seconds and take a look at it very closely. Starting from this molecule here, which is toluene, commercially available. By now, you should be able to do this. Design a synthetic route to this. So most of our discussion today will be centered around this synthetic design, in terms of the nomenclature of carboxylic acid, nomenclature of nitriles, reactions of nitriles, and synthesis of nitriles and carboxylic acid. Okay, so if you take a look at this here, how will you design the synthesis of this molecule, starting from here to here? I will give you a hint. This carbon here is this carbon. Okay. Anybody has an idea? Let us do this together. We want to go from here, from toluene, to this ibuprofen. We should be able to do this. We know enough chemistry now to do this. We want to do Friedel-Crafts. Where? Friedel-Crafts where? On the top group, okay. Let's focus on the bottom group first. Let's do the bottom group first. Okay, that's it. We need to do Friedel-Crafts. We're going to get to that. Let's do the bottom group first. As a synthetic design. Okay. This carbon is this carbon right here. So what do you want to do? What do you think we should do? The first thing we need to do, we want to functionalize this carbon. We would like to functionalize this carbon. Okay? Yes.
And then you want to make a new carbon.
Yes, excellent. We want to make a new carbon-carbon bond.
So I'm thinking of like a Gilman reagent,
like Gilman reagent or Grignard reactions, those kind of things, right? Huh? Use exactly. So you want to functionalize this with MBS? Excellent. Okay. So we will start with MBS. Okay, what would MBS do? Brominate this carbon here. Excellent. Very good. Okay, so we want to brominate that carbon. Keep in mind, this is a very important commercial drug that makes billions of dollars. So now this is an opportunity for you to design to design a new synthesis for this compound. Maybe you could make money doing this, you know. The pharmaceutical industry may call on you and say, wait a minute, this is a new process here. Okay, so we have this. Okay, so where do we go with that? Gilman, okay. You want to do Gilman reagent to then do what with that? Okay, you want to use that to add about, okay, if you make Gilman from there, what do you do? Yeah, that's, you know, you are on the right track, but about Grignard. Okay, make Grignard. Okay, we'll do Grignard. Is that right? Something? Okay, good. Okay, so if we do Grignard here, so we are going to form this. Okay, then what do you do with the Grignard? Isopropyl, propanol, very good. Propanol, exactly, acetone, great. Okay, so now you want to do a Grignard with a ketone, right? Okay, so you guys are thinking just right. Step one. See, people get paid millions of dollars to do this. So this might be your chance to design a new synthesis scheme for Advil, right? Then follow that up with what? Acid. Okay, so where does that take us? We form what kind of product? A tertiary alcohol. Excellent. We form a tertiary alcohol. Okay, then what do you do from there? What do you do? This is where we want to come here, right? What do you do? Oh, I'm sorry. Are we missing a carbon? Oh, yeah, that's right, that's right. So we now have this, let's see here. We have this here, CH2, and then C. Okay. Then what do we go from there? Dehydrate, okay, dehydration, okay, with what? Okay, let's do a couple of steps. POCl3, okay, phosphorus oxychloride, okay, very good. Then after that, hydrogenation, okay, good. So after that you do hydrogenation, and that will now give you this here. Okay, so far so good. We are on the right track. Then what do we want to do now? Fiddlecraft? Okay, You want to do a fiddle craft. Now you want to join. Okay, so let us do a fiddle craft. So we come here. Well, what do you want to use for your fiddle craft? Okay, you want me to give you a legend, right? Okay, I'll give you one. Okay, but this here. You use acetic chloride, right? Followed with aluminum chloride. Okay, so what does that give you? Give you a ketone? So we have this here, right? And then we have our ketone here. Is that right? Okay. So far so good? Okay, so now if we say this carbon here is this carbon. Okay, now what do we do? What do we do? Somehow we still need to form a new carbon-carbon bond, right? So an alcohol, okay, you want to go to Grignard? Okay, good. So at this point, let me make some room. So now we want to take it to an alcohol. What do you want to use to take it to an alcohol? Anybody? Sodium borohydride? Okay. Sodium borohydride. Followed by? Okay, good. Now, folks, keep in mind that when you do this, if all you do is just give me sodium borohydride and acid, I will take a point, because that will not work. You have to say step 1, step 2. Okay? Many of you did that in the past exam. Many of you could have done better, but you made those small mistakes. And if I did not stop it right now, you continue to make it. So, anyway. So, that would therefore give you for my alcohol. What do we now do? What do you want to do now? You want to make Grignard, you say you want to do Grignard somewhere, okay? To do Grignard, what do you need? PBr3? Okay, yeah. You could do PBr3 or thionyl chloride, any one of them will do fine. So if you do PBr3 or thionyl chloride, that will give you this here. Okay, now what do you want to do from there? Magnesium. Form a Grignard. Okay, good. Now you want to form a Grignard. Let me tell you this. Actually, this commercial synthesis of this compound, they go through this here. They actually make this for the commercial synthesis. So you guys are actually doing great. Okay, so now you want to magnesium, then follow with what? Follow with what? Formaldehyde? Okay. You want to form the new carbon-carbon bond? Okay. Good. And then step 3, okay. And so that will give us this here. Okay, this right here, and then this here, CH2. Am I alcohol, right? Okay. Now what do we do? Then go to do what? Oh, I'm sorry. I missed this. This is supposed to be here. Okay. Then you do what? Oxidation. Okay. Chromium trioxide. Good. Very good. Very good. Okay, so now we've made a new ibuprofen, which is Motrin or Advil. That's a very good route. Now, actually, the commercial process, what they do here. Okay, so I'm going to erase this. That is correct. You guys did just fine. For the commercial process, this is what they do. By the way, so what is done here, just to show you, this is one way of making carboxylic acid. Okay? So you take a primary alcohol, oxidize with chromium trioxide, and you get carboxylic acid. Now, for the commercial process, what they do, at this point, they take the alkyl chloride. Can you guess what they do to make this in the commercial process? You guys should know that. Any idea? What is today's topic? Carboxylic acid and Nitriles, exactly. Okay, so that's a hint. Okay, so you could go from a nitrile to carboxylic acid. So therefore, what do they do to get from here? The cyano group will act as a nucleophile. So what they do, they take this here, then they take the cyano group as a nucleophile, do an SN2 reaction on this. Okay, they do SN2 reaction on that to get this here. And the cyano group. Okay, once they get the cyano group, then what do they do? Go from cyano group to carboxylic acid, just do oxidation. You could oxidize cyano group to carboxylic acid by using dilute acid water. Okay? So now you see that all of those synthesis steps that we've given you, they actually do serve a purpose. Okay? So these are things that actually you could use to make very important industrial chemicals and drugs. So, like I said, this here called ibuprofen, most of you have used before. So during the course of the rest of this semester, we are going to be doing stuff like this, in which we bring in very important drugs or important molecules for you to actually use your synthetic knowledge to design. Yes.
If they're on the same organic molecule, what distinguishes ibuprofen from
Nothing. Just different manufacturer. They call it Motrin, Advil, the same thing. In Europe, they call it something else. You know. Okay, that's the way they do that. Actually, the patent for this compound came out in 1961, so everybody is making it now since the patent is already run out. Okay, so anyway, so this just gives you some idea that all of those synthetic methods that we show you, all of those reagents that we show you, these are really very important. They have very important commercial uses. So you need to know them. Because if you go to industry, For example, you get your PhD in organic chemistry, they start you off by giving you a salary of about 100,000 or more just to do this kind of stuff. Okay, so really, now you don't owe anybody you don't owe nobody any money at all, because we pay you to go to graduate school. But if you go to medical school, you owe about $1 million by the time you finish. Yes, I think here. Yes. That is to start. That is just to start. Oh, the $100,000 a month. Oh, I wish they did that. I wish they did that. No, it's $100,000 a year. Okay, anyway. So now what is done here is to show you the synthesis of carboxylic acid. Okay. We also show you the synthesis of nitrile. You could synthesize nitrile by simply performing an SN2 reaction on an alkyl secondary, in this case secondary alkyl chloride. Okay, now we also want to use this molecule here to introduce the whole concept of nomenclature. Now, supposing I ask you to give the name of this molecule here. When it comes to nomenclature of carboxylic acid and nitriles, just like other organic molecules, the nomenclature is derived from what? What is the nomenclature derived from? Just like the other organic molecules. From the corresponding longest chain of the corresponding alkane, right? Okay, very good. So in this particular instance here, if you look at this molecule here, okay, let's start with this very simple molecule. Talk about nomenclature now. Okay, for the nomenclature of carboxylic acid, if I have this, the corresponding alkane name for this molecule would be what? Corresponding alkane would be what? Propane. Very good. So to name the carboxylic acid, what you do, you remove the E ending of the corresponding alkane name and you replace with the suffix OIC. OIC. Then you add the word acid as a separate word. Okay, so this becomes propanoic acid. Propanoic acid. Now, if I have this, is that mine or yours? Mine. Okay, if I have this, what would be the name of this molecule? What would be the IUPAC name of this molecule? 3-methyl pentanoic acid? Okay, very good. 3-methyl pentanoic acid. So, in this case, the longest carbon chain is 5. Notice that we start counting the longest carbon chain from the carbon that contains the carboxyl group. Okay. Now, supposing now I tell you to name this molecule, this ibuprofen, this here. What is the longest carbon chain that contains the carboxyl group? What is the longest carbon chain that contains the carboxyl group? What is how many? 3 exactly. The longest carbon chain that contains the carboxyl group is 3. which is this here. This is carbon number 1, carbon number 2, carbon number 3. Okay, so what that tells us is that this here is nothing but a substituent. This is a substituent. So therefore, to name this, how are we going to name this molecule? We know that the IUPAC name, yes. What is it? Okay, what's the base name? What is the base name? Propanoic acid. Okay, let's do that first. Okay, so the base name is propanoic acid. Okay, now, since we have a complex substituent, we put them in parentheses. What position is that substituent? Position number 2. So we're going to have to say 2, then paren. This group here, this alkyl group here, this is isobutyl group. That is isobutyl. Iso because it's 4 carbon, and you have this is the iso group. This here is called, okay? Huh? Yes, very good. Thank you. We got to tell the position of that isobutyl group on the phenyl ring. So it has to be 4 because you have the phenyl group right here, and relative to the parent chain, the isobutyl group is on the 4th position. So therefore, because 4 isobutyl phenyl propanoic acid. Okay. Okay. So now, supposing we wanted to name, remember we made the cyan or the nitrile, okay, when we were trying to make the ibuprofen. Supposing, I also tell you, to name this, the precursor to that, which is this here. Keep in mind, we go from here to here by hydrolysis. That is how we got that. Supposing I tell you to name this, so now that will also now take us through the nomenclature of nitrile, because this is a nitrile. Now for the nomenclature of nitriles, let us start with a simple molecule. If we have this, this is a simple nitrile. To name the nitrile, what you do, you look for the longest carbon chain that contains the carbon of the carbon-nitrogen triple bond. And in this case, what is the longest carbon chain? What is it? 4. So you have to start counting from here, from this carbon here, 1, 2, 3, and 4. Okay, now to name this, you name this butane, you give the name of the corresponding alkane, you give the complete name of the corresponding alkane, so this becomes butane. Then you add the word nitrile, butane nitrile. That would be the IUPAC name for this molecule here. So become butane nitrile. Okay. So therefore, how would you name this molecule here? How will you name that molecule? What will be the base name? Propane nitrile. Excellent. Because you have 3 carbon atoms here. So that becomes propane nitrile. So that is, therefore, we have propane. Trying to get it, okay. Get this out of here. So that becomes propane nitrile. And then, of course, this here is your substituent, so now you need to indicate the position just as we did before. That is 2,4-isobutyl phenyl propane nitrile. Okay? Now, sometimes you could also say, for example, if we have this, supposing we have this molecule here. When you have this molecule here, you have a nitrile cyano group and a carboxylic group. To name this, you have to name this as a carboxylic acid. The carboxylic acid takes preference. In that case, this group here becomes a substituent. Okay, that becomes a cyano group. As we told you before, that becomes your cyano group. Just as you have your methyl group. So what will be the name of this molecule? This is position number 1, number 2, number 3, number 4, and number 5. So what will be the name of this molecule? 4 cyano pentanoic acid. Excellent. For cyano pentanoic acid. Now, if you are either the carboxyl group or the cyano group attached to a ring system, say for example you have this, cyclohexane ring attached to a carboxyl group. In this case, you give the complete name of the ring system and then you add the word carboxylic acid. So here becomes what? Cyclohexane carboxylic acid, separate words. Now, if on the other hand you have the cyano group attached to the ring system, okay, this here. Okay, here you call this, you give the complete name of the ring system, and then you add the word carbonitrile. Cyclohexane, then you say carbonitrile. Yes, yeah. If it is attached to the ring called carbonitrile. Now, if you want to name this the carbon nitrogen triple bond as a substituent, then you use the word cyano as a substituent. In this case, in this case here, it is a substituent. Yes.
Is it also 2 words? For cyclohexane, carbonitrile?
No, 1 word. 1 word, yes, 1 word. Okay. Now, of course, if you, yes.
So how do you know if it's like 6 presidents, like
oh, that's the convention. That's the IUPAC convention. Okay. Carboxylic acid takes preference over everything else. Over ketone, over aldehyde, over cyano. Okay. Now, if you have two carboxyl groups on the same molecule, say, for example, you have this. Okay. In this case, the longest carbon chain is this, right? So now you have to, of course, this carbon number 1, number 2, number 3, number 4, number 5, number 6. Okay, at this point, this becomes, you have to name the corresponding alkane. Okay, the corresponding alkane here will be 1, you have the cyclohexane ring, so we have to say 1,6-hexane dioic acid, di, you use the word di, so this becomes 1,6-hexane di, the word di to indicate that you have 2 oic. You use the word di to indicate that you have 2 in there. Okay. Okay, so that's all we're going to do about nomenclature. And so what I want to do now, I simply take you back to the slides to give you some of the examples that we just given you. For example, you see this here, these are all nomenclature, propanoic acid. This is 4-methyl pentanoic acid because the methyl group is in the 4th position. Here, because you now have the carboxyl group attached to the ring system, of course the ring system is cyclopentene. You name the ring system and then you add the word carboxylic acid. The same thing here, there is stereochemistry here. Trans 4-hydroxy, because this hydroxy group is trans to this carboxyl group. Trans 4-hydroxy cyclohexane gives the complete name of the ring system, carboxylic acid. And you can see here, also here, you have dioic acid here, and the longest carbon chain is 8. So you have 3-ethyl, because you have the ethyl group in the 3 position right here, 6-methyl here, and then the octane dioic acid. Notice here also that you have to follow alphabet types in order. The ethyls come before methyl. All of those things that we told you earlier with regard to nomenclature, you still need to observe all of those rules. Okay. This is just showing you an example of carboxylic acid. Okay, we will come back. Now, these are some common names for carboxylic acid. For the most part, we are going to stick with the IUPAC name. Of course, you already know this. This is acetic acid. What would be the IUPAC name for acetic acid? Ethanoic acid. But you see, the word acetic acid is such a common name that's been used for so long that nobody actually calls it ethanoic acid. Okay, by the way, acetic acid is treated in, do you know where you find acetic acid? Where? Vinegar, right? You know, use as your, most of you eat this every single day, right? Okay, so when you eating your salad dressing, that's most of what you eat in acetic acid. Okay. Anyway, these are some common names for common carboxylic acid. Of course, nomenclature of nitriles, we told you already. You name them as, you give the complete name of the alkane, then you add the word nitrile. Sometimes, as if you don't have enough rules to follow, sometimes you could also name the nitrile as a substituent of a carboxylic acid. In this case, the corresponding carboxylic acid here is acetic acid. So here, what have we done? We remove the word IC, remove the prefix, the suffix IC, and we replace with O-nitrile. So that becomes acetonitrile. Okay. The same thing here. This is from benzoate. The corresponding carboxylic acid here is benzoic acid. So we remove the OIC of benzoic and we replace with O-nitrile. These are all acceptable IUPAC names. Okay, now let us now finish up today's session with the synthesis of these compounds. We will deal with that later. You will find when it comes to the synthesis of carboxylic acid, most of this we've done already. Is this familiar to you? Okay, anytime you have an alkyl group attached to benzene and you have this reagent here, okay, as long as that carbon that is attached to benzene ring also is attached to an hydrogen atom, that carbon will be oxidized to carboxyl group, and that is what you find here. For example, if I take this molecule here, if I take this, and I use potassium permanganate, I will get benzoic acid. If on the other hand, I have this, and I take the same reagent, potassium permanganate, there will be no reaction. Okay? For this reaction to go, there must be an hydrogen attached to the carbon, which is attached to the benzene ring. In this case, we have this hydrogen here. At least one hydrogen attached to that carbon. Okay, so we could form carboxylic acid by the oxidation of alkyl benzene. You've seen that before. Another reaction that we've seen before, oxidation of cleavage, oxidative cleavage of carbon-carbon double bond. Anytime you have a carbon-carbon double bond in which any of the carbon-carbon double bond is attached to an hydrogen atom, that carbon will be oxidized to a carboxyl group. That's what you see here. Okay, this becomes this on this side, and this here becomes this on that side. Okay, therefore, supposing I have this, let's go to, supposing I have this. And I do this. What product will I get? What product will I get? What? It will cleave this, right? Okay, we will cleave this. We are going to cleave this. Keep in mind that this carbon here is attached to an hydrogen. So this carbon becomes a carboxyl group. And this carbon that has no hydrogen becomes a ketone. Okay? So therefore, you are going to get this. You get that? Okay? Okay, so now we're giving you two synthetic methods for carboxylic acid. What are those? Oxidation of active benzene. And what is the next one? Oxidative cleavage of carbon-carbon double bond using potassium permanganate. Folks, at this point, all of you should have your own table of reagents. That is most important, believe me. Do not use another person's table of reagents. When you make your own table up, you find that you get to know the reactions much better. Do not simply pick up somebody's table of reagents and you say you want to use it. It's almost like giving you another book to read. But when you make yours up, that is your own book. You tend to remember much better. So if you have not made up your table of reagents by now, please start doing it right now. And you find that those people who have done it, they find organic chemistry much easier to deal with. Okay? Okay, so now we have two methods that we're giving you. Actually, we're giving you three. What is the third method we're giving you today for making carboxylic acid? What is it? Oxidation of nitrite, exactly. So far we have given you three methods for making carboxylic acid. Okay. Another method for making carboxylic acid is oxidation of what? Anybody has an idea? Of primary alcohol, exactly. We gave you that also today, oxidation of primary alcohol. Okay, you could take a primary alcohol, and what do you need for that? Okay, chromium trioxide, right? Very good. Take chromium tri. All of this is done before, so this will be reviewed for all of you. That will give you a carboxylic acid. We could also oxidize aldehyde. We could also oxidize aldehyde to carboxylic acid using chromium trioxide. So all of this should be part of your table of reagents that you need to be making up. Okay? And aldehyde will be oxidized to carboxylic acid with chromium trioxide. Okay. Okay, another important method, which is really very, okay, I've given you this already, oxidation of primary alcohol, oxidation of aldehyde. I didn't even know I had this here. Okay. Oxidation of nitrite, we've given you that already. Now we could also use Grignard. Grignard is a very powerful reagent. If you take Grignard and you dump in some dry ice, carbon dioxide, you get carboxylic acid. Okay, that is what is happening here. This is carbon dioxide here. Okay, all they are doing here is showing you the mechanism. You know that the Grignard will act as a what? Grignard will act as a what? As a nucleophile. You have this carbon here, nucleophilic, comes in attack this carbonyl carbon of the carbon dioxide from this intermediate, and then you dump in some dilute acid, you get benzoic acid. So this is a very powerful method indeed. You could take, I could go from here, I use a Grignard reagent. Okay, I say step 1, carbon dioxide, and then step 2, hydronium ion. I will get, what kind of product do I get? What will I get? What is it? Tell? Yeah, what kind of carboxylic acid? Propanoid is for butanoic, exactly, butanoic. So actually, remember the synthesis we gave you earlier for ibuprofen, in which we use a Grignard reagent. We could actually continue that process by adding carbon dioxide to form the ibuprofen. So that is another way to make that particular product. So anyway, so you can see there are different ways in which we could make carboxylic acid. So far I think we've given you about 5 methods already. Huh? Okay, this is just something you want to think of. If you work in industry, the cost is very important. If we gave you these 2 routes here, going from here to here, what route will you choose? Which would be the more efficient route? And what would be the reason? Which would be the more efficient route? If I ask you to, you want to save your company money, okay, and then for those of you who are engineers, you also have to design the reactor to place the material in, so the heat of reaction and all those kind of stuff you have to put in place. But for you don't have to worry about all of those things right now. Okay, based on what you know right now, which method will you use? This method or this method? And why? Let's go by cost, just by cost. Huh? Okay, we have sodium cyanide, very cheap. I could pick up sodium cyanide anytime, you know. That's when it used to be I could. But if you pick up sodium cyanide now, the FBI will knock on your. It used to be very cheap. But if you pick up sodium cyanide now, the next day the FBI will be knocking at your door. So I don't know about that now. But it's cheap. It's cheap. Okay, so you do SN2 reaction, and then you use water. This is water. Okay, as compared to Grignard. Grignard is a little bit more difficult to make, but once you make it, it's very reactive, and it generates a lot of heat. So for those of you who are engineers, you have to worry about all those stuff. So I would say that this route, this here is probably cheaper. Okay, but sometimes industry doesn't go by those kind of considerations. They just go by what is easier for them to get money out of. But I think just going by cost alone, this here is probably better. Because magnesium is a little bit more expensive than cyanide. Carbon dioxide, even though it is cheap, you still have to freeze it. You know, how many of you have seen carbon dioxide before? Frozen carbon dioxide. Yeah. Okay, so you still have to freeze it, and then just dump it in. It's cheap, but it's not as cheap as water. Because this is nothing but water. Just add a little bit of acid to it. Okay. Okay. What time do we have? Oh, well, you've got plenty of time. We will finish this chapter today. Stop me 5 minutes to the end of class. Okay. Okay, now let's go to reactions of carboxylic acid. This was done also before. Reactions of carboxylic acid. We're not going to go too much into it because in the next chapter we are going to do some of that also. Reactions of carboxylic acid. Well, we have, if you take a carboxylic acid, you could react with thionyl chloride, you get an acid chloride. Okay, carboxylic acid reacts with thionyl chloride to give acid chloride. This is thionyl chloride. For example, we take this here. That will give you this molecule here. You could also take carboxylic acid and make an ester. We call esterification. Say, for example, you could take benzoic acid. I'm sure some of you have done this in the lab already, or if you have not, you are going to do it. Take benzoic acid. Have you done this in the lab? Those of you doing the lab? Have you done it? Esterification of benzoic acid. And you take, in this case, any alcohol, methanol, in the presence of some kind of acid catalyst. Okay, you form an ester. You form an ester. This reaction we refer to as Fischer esterification. Fischer esterification is a very important commercial process. All you need to do is just take a carboxylic acid, take an alcohol, and add some mineral acid to it, and you reflux for about 1 hour or so. And right? You know that experience, right? And then you get your ester. Okay. Now the mechanism for this reaction, we will show you the mechanism when we do chapter 21. Okay. There is another reaction we want to show you, the 3, called Hell, Bolhard, Zielinski. These 3 people discovered that this reaction, they all discovered it by the same time, so they are going to be given to the names of, the name has got to be assigned to all of them. If you take a carboxylic acid that has an alpha hydrogen, when we say alpha hydrogen, in other words, you have, this is the alpha carbon, and this hydrogen are the alpha hydrogen next to the carbonyl, and you take this reagent here. This is the reagent you need for this reaction. Phosphorus tribromide, in the presence of bromine, you will get this product, in which we replace one of the alpha hydrogen with bromine. So this reaction is actually very important in the sense that we use this to make amino acids. It's very important. It is an intermediate in the production of amino acids. So the point here is you take this carboxylic acid and this reagent here, phosphorus tribromide and bromine, to give an alpha bromo carboxylic acid. For example, supposing we have this. What would be the product? What would be the product of this reaction? Okay, this is the alpha hydrogen carbon here. So we do replace the alpha hydrogen. Very good. Okay, another very important reaction of carboxylic acid is the acid-base reaction. Actually, that's why we refer to them as acids. Acid-base reactions. Why are you laughing? Okay, acid-base reaction. If you take a carboxylic acid, say acid base reaction. And you take any kind of base, let us say we take sodium hydroxide, any sodium hydroxide in this case, or potassium hydroxide. This hydrogen here is very acidic. So we will be able to make this here okay, we make the carboxylate. So the sodium is somewhere just hanging around here somewhere. We make the carboxylate. Now, so we say this hydrogen is acidic. Now the acidity of any given molecule depends on the stability of the what we call the conjugate base. So this here we refer to this as the conjugate. The conjugate base, and therefore this is the conjugate acid. So if you take a look at any hydrogen attached to within an organic molecule, if you say that hydrogen is acidic, what in essence we are saying is the conjugate base of that molecule, once we remove the hydrogen, is very stable. Okay? Now if you take a look at this here, let us take a look at this. Acetic acid. Take a look at acetic acid. The conjugate base of acetic acid, if you have hydroxide here, will be here. We could actually measure the acidity of this particular hydrogen here, and the measurement that we use is what we call the pKa value. We could determine the extent of acidity, and the pKa value for acetic acid is about, for this hydrogen here, it's about, say about 5. Now, if you take a look at this hydrogen here, this hydrogen here, okay, because those are hydrogens also. The pKa value for this hydrogen here, this here, will be about 25. So in the order of trillions of times, several trillions of times more. This is a lot more acidic than this. The lower the pKa value, the more acidic the hydrogen is. Keep that in mind. The lower the pKa value, the more acidic the hydrogen is. Now the question now is, why is this here more acidic than this? Okay, because the answer is resonance. The answer is resonance. When we draw this, I could draw another resonance contribution for this molecule here, for this conjugate base, in which I will move this electron to form a double bond here, and this, so those negatively, those are the electrons who reside on any part of these three molecules here. So as a result of resonance, we say that the conjugate base of acetic acid is stabilized by resonance. On the other hand, if we pull this hydrogen out, the conjugate base cannot be stabilized by resonance, just as we've done here. Okay? So another aspect of the time we have do this, then we leave for the day. Okay. Another aspect of acidity, there are two factors that will stabilize the conjugate base. Two factors stabilize our conjugate base. One is resonance. The other is what we call inductive effect. Now you will ask, what is inductive effect? Inductive effect simply means the ability to pull electrons from one part of the molecule to another part of the molecule. It has nothing to do with resonance. Okay, it has nothing to do with resonance. Okay, now let us see what are the effects of this. Let me go back to my presentation here. Okay, look at the pKa value of all of this acid here. Notice here, the lower the pKa value, the more acidic it is. So what we are saying here, this is the most acidic of this series of compounds here. Okay, now let me go back. That was? Okay, good. Okay, take a look at this. Look at this molecule here. This is acetic acid. Has a pKa value of 4.76. Then when we attach chlorine, we replace one of these hydrogen with chlorine. Look at the pKa value is 2.85. In other words, it is more. This hydrogen now is more acidic than this hydrogen because we attach this chlorine to it. And that is the effect of what we call the inductive effect, because the chlorine is electronegative, it's pulling electron away from this side, from the conjugate base, thereby making the conjugate base more stable. Now when we add two hydrogen, we replace two of the hydrogen with chlorine, see what happens. pKa value goes down. So inductive effect again. Now we replace with all of the hydrogen with chlorine. Look at it. Okay? So we could give you different molecules and say which is going to be the most acidic. It's either the explanation will have to be due to resonance or due to inductive effect. In all of these cases here, these are inductive effects. Look at here, this molecule here, chlorine is here. On this carbon here, this is carbon number 1, number 2, number 3, number 4. Chlorine is on carbon number 4. Look at the pKa value, 4.52. Now, when it is on carbon number 3, getting closer to the carbonyl, it goes down. So on carbon number 2, it even goes down further. So inductive effect is very important here. So on this note, we come to the end of, I know you guys are tired by now. So when we come back, we'll finish up on chapter 20, and then we'll start with chapter 21. Okay, so in the meantime, just I will give you back your exam.